Hello. This is Chill Math Stream by popular request. I'm on the Murderous Maths website. I'm excited about this. This was voted Site of the Week in the year 2001, and since then it's got even better. It's like we've got a lot of maths that we can dig into here. Like Mountain Ash. This was Mountain Ash's doing, in a way. Good to have you with us, Mountain Ash. I don't know if you want to tell me which bits of this website you wanted me to do on the stream, but I've got some ideas. How's everyone doing? You alright? Hope everyone's alright at home. The content you're looking at, by the way, this website, Murderous Maths, is by Jason Poskett. There he is down in the bottom left. He's an author who wrote some books called Murderous Maths that are a bit like Horrible Histories, and Horrible Histories is having a bit of a moment, isn't it? Because it's a TV show in the UK at least, and it's on YouTube and stuff. But Murderous Maths was the one for me when I was a kid. The books have been around a while, and it's quite nice that he's still going. The website's still going, and there's some stuff to do. So we're gonna have a go at some of that on this bank holiday weekend. Hi Murray. Hi Ab. Yes, good. Okay, that is the whole concept. I'm a bit scared to click on stuff because who knows where it will take us on the internet or what it will do. Let's see what we can see on the page already. Everything, right? For example, over here, I can see. Oh, when you hover, stuff happens. Okay, one of those. It's also one of those websites where when you scroll, the background doesn't. All of the. Do you remember? Maybe nobody remembers websites being like this for a bit. Not so much anymore. It's got this really nice kind of mathsy background. I wonder if I can extract that. Maybe not. Do some extraction. Can I get the background out? That'd be fun, wouldn't it? Possibly I could do some sort of weird inspect element stuff. Script language, JavaScript 1.2. Okay, I'm probably not going to extract the background out of this website, but I kind of want it. Anyway, look, it's got all sorts going on in the background. There's like circles there. Some circles with a shaded region. Cube root of 3/8 over here. Oh my goodness. Yeah, there's a link to Math City, which is now open in Leeds. This website's being updated. Look, there's this fact about 2024. So when I hovered over this before, the link looked like it was about 2018. So I'm going to sanity check that. Okay, yeah, this is sort of safe. Let's go over here first. I also saw this tricks bit up here. It caught my eye. I love some tricks and games. That's very me. Very chill. Less so on Pongo McWiffy's A to Z, but we'll get there at some point. Okay, what are we learning here? Oh, okay. We've got logos with a cute fact about each year number. Even more fun than counting to 1,000,000. Yep, this is a good fact. Tetrahedron numbers. We've got a little demonstration of what tetrahedron numbers are. So it's pretty efficient maths education, isn't it? Oh, and look, this is pretty good. Oh, I didn't know this fact about 22. What is that then? That the square of 22 is the sum of 3 squares? Is that unusual or weird? I kind of know some facts about sums of squares. Sum of 3 squares I think is a bit unusual. Oh yeah, I am back in. Great Wave Jumper, Great Wave Mug, having a wonderful time. Current craft project, Charlie, is where I am trying to do a kind of cross-stitch bookmark thing. It is also the Great Wave. Maybe I'll show chat when it's in any sense finished. Yeah, so this 2018 fact down here looks good. The biggest challenge until we discovered this. Okay. Oh my goodness, there's some restrictions. So I've seen necklace things like this before. On Maths Club, I've seen a proof that. Oh, was it the start of this year maybe? A proof that a to the p is a more than a multiple of p using necklaces, but this has got extra restrictions. 9 beads, 3 colours, and you have to use each one. At least 1 bead of each colour. And rotations count the same, I think. Let's read on. Okay, so I'm going to read this thing about 2018. This seems like fun. Oh, Charlie, am I doing repetition and chaos? Oh, cool. Yeah, that's something that I do sometimes. I think I'm visiting some schools or something, and I'm doing repetition and chaos in, gosh, a couple of weeks now. I won't say where you are, because that feels like not how people behave on the internet. But I'm going to several schools coming up soon, and I'm doing the normal talk I do is called Repetition and Chaos. If you search all the way through the archives, I've done it on the internet a couple of times as well, but don't do that. Let it be a surprise. And if other people in chat have seen Repetition and Chaos, a audio-visual experience, no spoilers. Okay, so what's going on here? So 3 to the 9 is apparently 19,683. But then they're going to use 2. How many of these? Only use 2. Okay, there's these ones. Good. Now 9's not prime. So if we're going to do some allowing for overcounting, yeah, I can see that coming up on the bottom of the page. We're going to have to allow for things that rotate by a factor of 3. Or yeah, overcounting, then realising you've overcounting and saving it. So there's going to be some big division. Maybe not. Yeah, okay, so subtract the ones that are just 2 colours. This is still just powers. But add 3 back in because you subtracted them 3 times. Inclusion, exclusion, brilliant stuff. 3 colours, good. Yeah, most cases, this is what worries me. A lot of the overcounting arguments that you do, you want to just say, in all cases, I've overcounted by a factor of 9. Here, I don't think they're going to say that. Yep, okay, I'm two lines ahead of the text on screen. Yeah, that is a problem. Some that repeat in a 3-bead pattern. Only 2? Only 2 repeating in a 3-bead pattern? What's going on there? You've got to use all the colours. You've got to use all the colours. That's pretty good. So you add those back on or something. You subtract it, divide. Oh my goodness. Yeah, okay. So I've seen things like this before sometimes, where you have some special exceptions. You subtract them. The other ones genuinely were overcounted by some factor, and then you add back again. Nice. Good stuff. This is all related to something that I've done. I did a talk in a school once that didn't go very well on counting necklaces, because there's a different way to do this that's a bit better. In some sense, it's more general. It doesn't make the calculation easier. It just generalizes nicely so that you do less esoteric kind of operations each time. And that's to do with the average fix. And I've had a couple of attempts at explaining it. I think once on Maths Club that was not very good. Yeah. What are you going to tell me? You're going to tell me about reflections? Yeah, clockwise. Yeah, you can't divide by 2 because there's some that have reflectional symmetry. Oh my goodness, off you go. Yep. So you throw extra symmetries in, then your overcounting is different in lots of different ways. Yeah. So there's a group theory way of doing this that's really good. And the maths is really nice, but I've never managed to explain it well. It's, I guess, not really my area. And it's hard enough that I can't get away with it. Yeah. And don't worry, Charlie, repetition and chaos is my sort of thing and does go fine. So we're calling them 3D necklaces if you include turning it over. It's kind of reflection, which is fair enough, I guess. Let's try and put some maths on the screen. because I've sort of mentioned this. Yeah, okay. Let me tidy this link up. So the thing I'm thinking of is sometimes called Burnside's lemma, which is a bit weird because Burnside's link to it is that Burnside quoted it in a book, which is just mad, right? Somebody else proves it. Burnside mentions it. Now we call it Burnside's lemma, or some people do. It's really good. So in this sense, the word orbit here is the places that you can go to. If you've got a collection of points, when you apply a group, I'm not using the right words. Here we go. The way these work is you have a big overcounting exercise. So you have a set with lots of points, and then you realise that some things are the same under certain operations. So maybe you decide that rotating a necklace would count as the same. So that kind of connects together two of these points in your big set of overcounted things. And then maybe you decide the reflections count as the same as well. So that connects a bunch more of these things together. And punchline, because group theory is nice, there's structure to these connections. Instead of being a complicated graph of connections, if the operations that you're using form a group, then the kind of places you can get to form this nice complete graph. You can get from one to the other anywhere you can get to directly by doing some weird combination, rotation, reflection, which is in your group because of closure, but also because rotation and reflection gives you a different sort of reflection. So in some way, if your operations are nice, like you're considering all of the possible reflections for your necklace, then you have this kind of group structure, which gives you nice, beautiful graphs of which things are connected and considered the same. You want to count how many of these sort of orbits or clusters you've got, because you're considering each of those to be just one necklace, really. And there's a nice formula for it, which relies on the fact that there's this beautiful structure. It allows for the idea that you have different amounts of overcounting in the different bits of this graph, different connected components. So there's nice sort of like lightly graph theory, quite a lot of group theory, and it helps you do combinatorics counting problems. That's the sort of thing where I think it's the sort of maths that I want to explain to people in schools because it's nice, right? It links together lots of things, but I've just found that it's slightly too hard to actually, slightly too hard for me to explain anyway. Which is why you end up doing calculations like this, where you allow for everything individually and quite carefully, which is not a million miles different from the Cauchy-Frobenius lemma way of doing these things. Anyway, good. That's a good 2018 fact. Can I get some other facts? Oh, these are all. The other ones are all kind of self-explanatory, maybe. 2017. So this is just that 2017 is part of a Pythagorean triple. Is that something about the sum of two squares? Can't remember. Chat, do you know anything about Pythagorean triples? I should know about Pythagorean triples. 3, 4, 5, 5, 12, 13 is one of them. 5 and 13 are both sums of two squares. Have I just made that up? Is that a real thing? Yeah, 3, 4, 5 is one. Complex number plane thing, yeah. Complex numbers with integer real part and imaginary real part. Anybody? Integer real part, integer imaginary part. Yeah, there's a way of generating them all from that, isn't there? I think there's a general formula. I'm going to try and write it on the board, and then we can try and look it up. That's what we're doing. We are using this to learn and grow. Learn and grow. Right, whiteboard. Have I got a pen? I do not have a working pen. Okay. Turn it off and on again. Or I would like to be able to explain the Taniyama-Shimura conjecture without just saying there's a bit of maths, and there's a bit of maths and they're the same. I've seen the documentary and I can't help. The documentary is very nice, if we're thinking about the Fermat's Theorem documentary. I don't know what that is, though. Hello, Super Snowman. See if I can remember some Pythagoras stuff. So I think the result is something like there's a general solution that's like this. And the bit I remember is that this is on the hypotenuse. Let's see if I can work out the other ones. And this is like this. So then the bit I can't remember is what to write over here, but I can work it out by remembering what Pythagoras is. So I'm going to start writing my justification. So this always works because I can't quite remember what to write over here, but I'll have a go. This thing is m squared minus n squared plus something else squared. Now let me have a quick think. 2m squared n squared is the cross term over here. And that's going to be a minus 2m squared n squared. So if I write 2mn in here, yeah. Okay. There we go. Hide your working out. Good. So that always works. I think that might be all of them. Or maybe, what do I think? Oh, okay, so this tells me that if your number is the sum of two squares, there's a Pythagorean triple for that. Is 2017 prime? I should use one of my factorization tricks. I could just Google it. 2017 is prime, and it's one more than a multiple of 4. So I think that means it is the sum of two squares. Yeah, people who know the most. There you go. Oh, factorization trick. On the work stream for a while, we were looking at ways to factorize numbers, and my favourite one at the moment is you do something like this, and you're looking for a square number that's bigger than 2017, such that this difference, so I think 45 squared is this big, such that this difference is a square number. And if that doesn't work, you go to the next square. And if you keep going all the way, if you keep going, you either find a factorization or you get to the point where you're considering, oh gosh, I can't remember when you stop, but I guess you stop. If the number's actually prime, when can you stop? So we're considering, because if this factorizes as a square number, then we can rearrange it. So if this was, I don't know, 3 squared, maybe it's not, but if it was, then it would be 46 squared minus 3 squared would be 2017, which would then be really cute because we could factorize like this. I mean, it's not equal to 3 squared, so none of this is true. If it did, then it would factorize nicely. So it's a factorization trick to try to find a difference of 2 squares that gives you your number. So I guess you stop if 46, if the factors are getting to, when you stop. So worst case scenario is it's got 2 factors that are very close together. No, that's good. I guess you stop when the leftover square, you stop when these things go negative. So keep going until you get to, what do I want? So I keep going until this n squared take away 2017 is like, if the leftover bit would also be bigger than, eventually the leftover bit is also large. It's never that big, is it? Oops. What am I doing? I guess worst case is if there's a factor of 2 and some other huge factor. It's very nice when it works. It's not very good if the number's actually prime. So there's one on the live stream last week. We were looking at the number 999, and that's actually quite weak to the attack of remembering that 1024, which is slightly bigger than 1000, is 32 squared, and the difference between 1024 and 999 is 25. So this gives you that 32 minus 5 times 32 plus 5 is 999. I think. This doesn't look right. No, it's good. So it's 27 times 37, which is not too bad at all. And saves you having to do any sort of division by 3 or something. You just check some square numbers nearby. This was sort of hidden in the live stream last week, but never mind. The Sunday stream where I just sort of poke holes in whatever I did during my job this week. If you've just joined us, hi, I'm James. I have a bit of a weird job where sometimes during my job I do a live stream about maths, and this is my sort of personal live stream at the weekend where partly I think about how that went. Also partly get on with some other maths. Back up here, I was talking about Pythagorean triples. I haven't proved that they all look like this, and in fact they kind of don't. Because I could multiply it up. Multiply the size. Mary doesn't like it when I talk about not being good at my job. Cheerleader, let's go. Have I done anything on this before? Have I told you why this is true? I think there's some sense in which this is all of them. I don't know if people have seen that before. I don't want to bore people, but I know a good bit of maths for why this is true. Which I will only do if there's popular demand. Herb says I haven't done it before, that's good enough for me. It's a good bit of maths. I will sell it to you in a second. Really would like to get this working. This is kind of alright. My limits. There we go. Okay. So maths works like this. He says, trying to remember the maths. Yeah, okay. So, if you're looking for whole numbers, a squared plus b squared equals c squared for your Pythagorean triple, like 3 squared plus 4 squared is 5 squared, then something you might try, this is quite hard, but what if instead you look for rational numbers? P squared plus Q squared equals 1. Because then if you've got some rational numbers like this, maybe I'll write them out as, I shouldn't have used P and Q, because now what am I going to call my fraction? M over n squared. You can sort of multiply up afterwards. You can turn your rational solution with fractions. I need 2 more letters in a hurry. K and F. You can multiply up by, a worst case scenario, I think like n squared, f squared. Maybe you don't even have to multiply it by that much. But you can always get up to something like mf squared plus kn squared. It's n squared, f squared. Nice. I mean, of course, if you had any solution to these whole numbers things, you would discover that if you found all the rational solutions. Because conversely, any solution to the whole numbers, thank you for R and S, that would have been really good. Would find or something. If we had all rational solutions. So we're not going to miss any. We might introduce some sort of weird solutions with rationals where I also have these, but I don't know, written in some weird format that I don't spot the common denominator or something. Yeah, I suppose if you started with the correct solution to this equation at the top, 6 squared plus 10 squared equals 8 squared. Nope, 6 squared plus 8 squared is 10 squared. And then you divide it by 10, then you would get to the same values. You get to the same values as if you'd started with the 3, 4, 5 thing. Yeah. Ooh, what is this? Pick a random Gaussian integer and square it so that its modulus is an integer. Hence a Pythagorean triple. Yeah, okay, that's a good strat. I like that. So pick your favourite one of these and square it. So I'll get 3 plus 4i, and then it's from doing my squaring, 4 take away 1 is 3. Good. Welcome to the show. And then take its modulus. Oh yeah, so then its modulus has to be, its modulus squared. Oh right, okay. So the modulus of this thing on the right hand side that a cool person's given me is, I was a bit worried it would be a square or something. Of course, the modulus of this number is the modulus of, so if this is A, this is Z. To get from A to Z, then this fact or something. And that's just the sum of the squares of the things we started with, so it's a whole number. I'm experimenting with saying Z. I'm not sure if I like it or not. Anyway, so this is going to give me that 3 squared plus 4 squared is 5 squared. That's pretty good. I like that a lot. So if I generalize that, so if I kind of eliminate the complex number element of that, then the solution you've described is this. What if you multiply the complex numbers? So if you had to shortcut this without saying any i's, you might say, well, pick numbers m and n for the components, and when you square it, you'll get this number, which will magically turn out to be part of a Pythagorean triple. And that is true because it is this algebraically. Always works. Good. I haven't thought of this as being the real and the imaginary parts of the square of a Gaussian integer before, but hey, that is good. Yeah, so you choose one big complex number, or equivalently, 2 massive real integers, and go for it. Yeah, okay. So I'm going to try and convince you how to solve an equation like this one up here, where we're looking for rational numbers that square and add to 1, which geometrically, it's a geometric method. Oh, not over there, not over there, never over there. That's why we keep things like step questions. Okay, so I need a circle. I'm trying my best to use features of Miro. There we go. Okay, so I've got my circle. So we're looking for points like this that have rational coordinates. And you've met some of these before, right? So 1, 0 has got rational coordinates. But there's also interesting ones like, oh, now I've got to be interesting, a new challenge, 3/5, 4/5. And other kind of Pythagorean triple inspired stuff exists somewhere on this circle, including negative numbers. But chill maths, I'm not going to label any negative numbers right now. And this is the circle x squared plus y squared equals 1. The brilliant idea for finding rational points works like this. Consider the line that goes through 1, 0. Or I say the line, but consider a line that goes through 1, 0. Are you going to help me out here, Miro? There we go. A little bit thicker. And pink. Okay. Consider a line that goes through here, and I think I want it to have rational gradient. So consider y equals mx minus 1 with m rational. Find the other point of intersection. With the circle. That's it, by the way. That's the whole trick. Because if there's another rational point over here somewhere, then the gradient will definitely be rational. So we'll find it for some value of m. We will find this. find this particular line that goes through that mystery rational point, and also 1, 0. But also conversely, and this is a little bit powerful, when you're solving this style of equation, linear and a quadratic, simultaneously, the steps you might do are to plug those things in, plug the second one into the first one. This is a polynomial with rational coefficients. So the product of the roots is rational, but one of them's 1. So you've got this polynomial where the last coefficient, the constant coefficient on the polynomial, is a rational number, and the leading coefficient is rational. A bit complicated, like 1 plus m squared, and the other things like 1 minus m squared or something like that. But that means that the product of the roots is rational. According to this, like if you imagine factorizing it, then the last coefficient of the polynomial corresponds to the product of the roots. That's somebody's law or something, Vieta's formula or whatever. But also it's just kind of obvious if you think about factorizing the quadratic. And that's surprisingly powerful, that observation that the product of the roots is rational, if you know one of the roots already. So if you know that there's this solution over here at x equals 1, then in fact the product of the roots is the other solution. They're 1 and something, and they multiply to give you this number. So this quadratic actually has pretty obvious solutions in some sense. Let's factorize it. So it gives you every rational point on the circle. The, I guess, slick way of saying this is that the rational points are in one-to-one correspondence with rational gradients, values for m over here. For each value of m, you get a rational point, and for each rational point on the circle, you get a value of m that's rational. So instead of varying both numbers, you go around the circle trying to make sure you stay on the circle and you keep both values rational, you can just change m. And this gives you a formula, right? Because you can go and solve this. And it gives you the formula that we already saw a couple of times. Something like this, 1 plus m squared x squared. And then, how much of this am I going to write out? 2m squared x. That's something to do with the sum of the roots. And there's minus 1 minus m squared. And I've messed up, it's a plus m squared. There we go. Okay. So this factorizes really nicely. I say really nicely, can I actually do it? Yes. Yes, I can. Believe in myself. What are we doing? So 1 is a root. It should be a root anyway. Yeah, the 1's cancel and the m squares cancel. And the other root is going to be, oh my goodness. If I divide by the 1 plus m squared, then the product is looking like this. Looking like this. I think it's this. I should check that that actually factorizes. I did that a bit too fast. If you're playing along at home, you might like to help me check that multiplying these things out does give me the right thing. I'm quite lazy. M squared minus 1, the plus sign comes from these two minuses. M squared minus 1, that will multiply by m squared plus 1. That would match up this coefficient. The leading coefficient matches. Can't quite be bothered to check the middle one. I should do better. It's chill maths, but you know. So there'll be a minus x, and there'll be a minus quite a lot of stuff. But then if I add 1 to this, I'm adding m squared and a 1, so the 1 will cancel with the minus 1, I'll get 2m squared on top, and there's a 1 plus m squared to cancel the denominator fraction. It's going to give me minus 2m squared. Good, okay, so that all works. So there's my other rational point, and I can change m, make m a different rational number. And maybe you can see it's got this sum of two squares, difference of two squares thing going on inside it, especially if I write m as something like, I don't know, I sort of always need more letters. Maybe it's time for R and S now, for this rational thing where I'm changing the numerator and denominator. Technically I'm supposed to say that those are coprime, I suppose, have no factors in common, because gives you different things. So this. So that's a rational point. It turns out the value of y is, I guess, unsurprisingly, something like 2rs, plus or minus, I think, because the circle's got this kind of symmetry to it. Do I believe that? Not really. Plus or minus, depending on the sign of m. So I'll put a little plus minus sign over here to say that I did think about plus minus, I just didn't necessarily get them all right. And then this turns back into the same solutions that we had before. Pythagoras via geometry, which is nice because Pythagoras is about geometry. But it goes via whole numbers, rational numbers, this kind of algebraic geometry idea, and then go for it. Yeah, pick a rational number m. I've written mine as r over s. Plug it into that formula. Find y, which I did in a kind of sloppy way. Yep, and then it's correct. And you can cross multiply by the denominator, or if there's some shared factors, possibly because there's something about odd and evenness going on here. But if things turn out to have a factor of 2, then don't sue me. Just track those carefully. You have to be a little bit careful if you're trying to do a rigorous proof that you found out exactly all of them with no double counting or something. You have to be a little bit more clear about what you mean by that to avoid the kind of 6, 8, 10 problem that I had up here. It's my job on this show to kind of point at problems, I think, and say, whoa, watch out for that. But chill. The fun idea is that the lines with rational gradient correspond to the rational points on the curve. You can do this for other curves. You can do this for other problems. It's a whole thing. So if you want to solve a slightly different equation, then maybe you've just got different numbers in here. Maybe you want to solve, I don't know, x squared plus 2y squared equals 1. No big deal, that's just some sort of ellipse, but it's almost like the shape sort of matters, I guess. Algebraically, when you plug this in, you're going to get some sort of polynomial with rational coefficients. Go for it. What you need is at least one starting point. At least one starting point. And then you need to check that when you solve the simultaneous equations, you're going to get a polynomial with rational coefficients in, and then you can play this trick. So it's something like if you have an equation like this that's quadratic in x and y. Let's try and say something true. A quadratic in x and y. Then what do? You can always do this. It's fine. If you have one rational point, you have infinitely many rational points, because you can generalize to find other ones. This is from the start of a book that I like. There's also, well, I haven't got very far with the book, but it's free online. The book is pretty good. Let me try and find the website for it. And now I have to try and find the correct website for it, because there are many. Yeah, okay. So it's recommended to me by a graduate student at Oxford who I bumped into. And they recommended this book called Topology of Numbers, which, yeah, it's about 350 pages and starts with some stuff about, that's a good picture. It has a lot of stuff about continued fractions. It has a lot of stuff about number theory. And it starts with, scroll. It starts with a preview for Pythagorean triples and this calculation that we've just done, reflected in the line x equals y or something. And if you want to see the proper proof with all of the care and attention to actually get all of the odd evenness stuff right, to make sure we find all of them, then you can find that here. And also 350 more pages of number theory done with interesting pictures. Good, I'm scrolling too fast for you to read Topology of Numbers. That'd be nice, wouldn't it, if I could just chill maths, we just ingest PDFs. Here it goes. Oh, that looks nice. Rational points on quadratic curves. Here you go. It's the thing I was trying to say. And then I got really worried. This is why you keep looking things up. Good. It's a throwback to number theory live streams. And also, yeah, it is number theory. Where's this book going? Ooh. Ah, Fermat's last theorem. But not really. Fermat's last theorem is equivalent to the statement that these curves have no rational points except their intersections with the coordinate axes. Help. Isn't that just... So now I've tricked myself into thinking that it looks fine. Yeah, these curves have come up in math questions because of course they have. They're just nice, right? So everyone should have a nice experience with a squircle at some point. Everyone should have this experience, he says, frantically making sure people have this experience. Right? If you have this circle, and then if you change the number n, you get different caps, like this thing. Or the even ones are nice because they give you these kind of shapes that are almost square with rounded corners. So you make this some sort of large even number, you get these kind of squircle shapes. They're nice. And if we could find rational points on here, so a point with both coordinates rational, I don't know, I'm zooming in as if that's going to help me decide whether it's rational or not. If we find a point with both numbers rational, then that would be a counterexample to Fermat's last theorem, because we would multiply it by the denominators, and we would get some lovely sum of two nth powers being an nth power. So in some sense, Fermat's last theorem is a very precise statement about these curves. But I don't think people actually think of it like that. Other non-integer values are also quite fun, but so we have one on a mock exam for Oxford at the moment. Right, you kind of want to put mod signs on, I think, for if you're going to play around with square roots and stuff. So if you do square roots, you get this nice kind of asteroid shape. I think it's called an asteroid. It's a good shape. And curves inwards. This is, oh gosh, is this the one that you get with a rotating line? I can't remember. It's either this one or the one with 2/3, which is subtly different. One of these is the line that you get when you have a ladder falling down a wall. Such a classic question, I suppose. No, I feel like that one might be the parabola sort of one. Anyway, I'm distracting myself with other shapes are available. Definitely feel like I've talked about these at some point recently. Oh yeah, tried to make a Christmas card out of them. That was fun. So yeah, try to make a Christmas card. To get more points, what you can do is you can apply a conformal map. So the thing I wanted to do to make the star more pointy, I was trying to make a Christmas card. To make the star more pointy, I wanted each complex number in the Argand diagram to look back, I suppose. No, I wanted to square each complex number. Yeah, if you square the complex number, then, well, as you walk around the star, the square of the complex number will go around twice as fast, because, oh gosh, if you write it e to the I theta, then the square is e to the 2I theta, so it'll go around twice as fast. So if you kind of replace the x and the y with the real and imaginary parts of the square of the complex number, so the process goes, instead of take the real and imaginary parts and apply this formula for the real and imaginary parts, but first square the complex number. So if I do something like this, well, that's already good. 2xy. Then you get something with twice as many points on it, because the coordinates x and y are kind of getting squared as a complex number first on the way around. So you can go round like that. Yeah, asteroids without an e, not to be confused with the large rocks, which are not to be confused with meteorites, which are not to be confused with meteors. I've just googled for the wrong one. Yeah, we got a citation for this. Oh look, okay, Wikipedia will help me out. Right, so asteroid turns out refers to explicitly the one with 2/3 up there, and it is the, oh no, what is that? What is going on? Tell me about a ladder falling over. Ugh, nobody's telling me about a ladder falling over today. They're telling me about spirographs. So what's the ladder falling over one then? feel like we're on a tangent to a tangent to a tangent. Is the ladder falling over 1/1/2? Is it this one? Envelopes. We've got some envelopes here. The common envelope of a family of ellipses of equation blah, where a plus b is 1. Don't think that's my ladder. Let me draw the problem I'm thinking of. So the problem I'm thinking of is a bit of a classic, which is why I expected to see it on that page. You've got a ladder. The ladder falls over, but don't worry, it's not a dynamics question. It's not a mechanics question. Nobody's going to do any vectors today, Charlie. As it falls, so this point's going to go down and this point's going to move over. I don't care how fast it falls or something. I'm interested in the kind of area that it sweeps out. So the bit that is at some point underneath the ladder. There are some points that are obviously underneath the ladder, like stuff over here. And there's some points where you sort of think, well, maybe if the ladder falls over, like that, there's some sort of curve to this. It's not quite the same as the ones that you draw where you connect the dots. It's not quite the same as this one where you connect the dots like that, moving one point over here and moving that point out at the same rate, because those lines don't all have the same length. So, how am I going to do this? We've only clicked the top left link on the maths page. Oh my goodness, you're right. My browsing history is just going across. Let's sort it out a bit. So we went here, and then we did this, because we saw a 2017, we saw this 2017 triangle, and then we went to talk about Pythagoras, and then we did some algebraic geometry sort of stuff, algebraic topology or whatever. Then we looked at this, we saw Fermat's last theorem, and we started drawing squircles. We remembered you could change the parameter and get other shapes like the asteroid, and then I remembered that one of them is sort of related to a ladder falling over. Is there a name for the connect the dots thing? I'm not sure. I've seen it called curved stitching, but that's because I've seen it as a kind of needlework exercise on Vicky Neal's page. We'll quickly pull it up. See if we can get the pictures. What am I thinking of? There's the curved stitching. There's the curved stitching. Quickly. So if you have a different angle, you get different shapes. It turns out to be a parabola for the one where you work along same amount, same steps on each side. But if you follow other rules, you can make other shapes. I'll leave this here as a kind of ideas about making Christmas cards, which I took from Vicky Neal. Even an IRL 3D version. 3D. There's an artist called Barbara Hepworth. Whose art you might be interested in. That's an E. Some of their art involves strings in 3 dimensions doing different things. Between 2 planes instead of between 2 lines. Ooh, so you could have the endpoints on one moving around on one plane and the endpoints on the other moving around on the other one. There you go, all connected. I'm not sure I want to do this ladder falling over problem. I think I've described it. You've got a ladder of fixed length, and as it slides down, it will trace out those other points. I guess this side is at 0, y, and this side is at x, 0, and the rule is something like you need x squared plus y squared to be L squared. Oh, I've seen that before. It's Pythagoras. For which? Explain that terribly. Because I don't want the points x, y. I shouldn't have used x and y. Right, cool. I've made a mess of that. I'm going to leave it there. But I've been reminded by Mountain Ash that we should get back to talking about Madras maths, right? Look at these other facts. We were only on 2017. I kind of skipped the 2016 fact. If you've just joined us, we're looking at the Madras maths website where they have a fact of the year. every year. We're going to look at the 2018 fact, which involves lots of overcounting. We briefly thought about the Cauchy-Frobenius orbit counting lemma, and then we noticed a Pythagorean triple, which I think I've now convinced myself that anytime the year is prime and one more than a multiple of 4, they'll be able to do something like this. And some other times as well. Not all the time. Not everything is the hypotenuse of a Pythagorean triple. Okay, good. What is going on here? 2019 is the first 4-digit sequence to appear 6 times in pi. That's not a terrible fact. Yeah, I'll take that. 6 is a bit specific, but I suppose, you know, the first, can we infer that the first 4-digit sequence to appear 5 times is something else? Not as good. Yeah, if it was the first sequence to appear 5 times, you would say that. So some other random 4-digit number might be that. This 2020 fact is a bit... I can't quite read. What's going on here? 2020 is made up of 2 zeros, 0 ones, 2 twos, and 0 threes. So it's Justin Poskett, the person who wrote the Merger of Math books, who taught me the incredible maths facts that 4 is the only number in the English language with the same number of letters as the number itself, which is pretty good as a fact. And later, I think in the same book, that 40 is the only number in the English language that has its letters in alphabetical order. So I know he's into this sort of thing. But still, this is very hard to pass. So 2 zeros, 0 ones, 2 twos, and 0 threes. It's one of those things you read it and you sort of think, is that brilliant or is that stupid? And I'm not sure. Are there any others of these? Wait, 2? No, okay, I'm so confused. It's made of 2 zeros, which is cool because that's the first digit of the number 2020. Oh my goodness. 4 and 40 are both classics. And yes, I've seen a Numberphile video about other languages. I can't remember who's in it. Is it a Matt Parker or a Ben Sparks kind of thing? Anyway. Okay, this one is somehow hurting my brain. It sort of sounds so silly, but also could be the only thing that does this. Okay, what if it had A zeros? Then A would also have to be the first digit. Oh no, I could just call it brilliant. Linguistic stream. If you want any linguistics recommendations, there's probably other streams that do that better than me. Then you've got a fact about palindromes, which you can multiply it by its reverse and you get a palindrome. I'll take that. It feels like that happens quite often, maybe. 1001 times 1001 is 1,000,2001. Hey. Am I surprised it happens for 2021? Yeah, a bit, I suppose. Is it something to do with carries? Get interesting number facts for other languages. Okay. The Numberphile video does have facts about other languages in, so if you're lucky, it might have facts about your language, or first language, or something. Okay, so I quite like the 2017 fact because it speaks to this kind of sum of two squares thing. I'm less keen on the things appearing in pi or being self-referential like this. This one seems to be that something is, well, this is like a Pythagorean triple in 3D, so fine, okay. I don't know about those. What can I do about those? I don't know anything about those. I'm not sure I can adapt my previous trick. I'm not sure I can adapt my trick to, I don't know, consider the sphere x squared plus y squared plus z squared equals 1 and to take a line through point, because That's going to intersect with the whole. It's going to intersect. I don't know a way to find these. This is cool. Isn't there a fact that everything's the sum of 4 squares though? So at some stage the party's over. Whose theorem is that? Lagrange's 4 squares? Oh goodness me, you can't just search for half the words that you're thinking of. Is it Lagrange? Yeah, Lagrange's 4 square theorem. This has definitely been on, I don't know, maybe the work stream or something. This idea that any whole number can be written as the sum of 4 squares. Okay, almost there through the years. 2023 is the product of some numbers. What are they going to tell me? 17 and 7. Oh, this is feeling a little bit more like numerology or something. I guess that's quite nice. You've got the squares of the digits added together and the sum of the digits. It's not quite numerology. It's prime factors. That's nice. And a slightly tenuous link to the numbers themselves. How hard is the proof? Quite hard, I think. By my standards anyway. And again, number theory is not quite my thing. Not at all my thing. I don't think I've seen a full proof of the 4 square theorem. Maybe that's lack of trying. Which numbers can be written as the sum of 2 squares is already hard. My feeling is that the 4 square thing's harder. I suppose I don't really know. Challenge for chat. The Lagrange's 4 square thing. I've lost it. Okay, 2024 is a good one. It's a tetrahedral number. Okay. Right, that was first link we clicked on the Murderous Maths page. We got 1 hour out of exploring this. Links to Math City. Then I guess I'm quite tempted by tricks and games. Let's give that a go. Oh, okay, right, it's different. Okay, I found the best page on the whole internet. It involves some. What are these? The trick with 4 cutout cards. You pick a number and is this like a web app? Oh, and it might have to print something for this. Oh my goodness. Lay out these 4 special cards with, hang on, what's this design? What's going on here? So this top one's got the numbers 1 to 8, and then upside down it's got the numbers 9 to 16. Our pulling about 3 years. It was quite a busy website. And then what is this? Make sure the secret number is the right way up on each card. Oh my goodness. Stack them up. Don't rotate them. So they make sure it's the right way up. So they maybe turn this one upside down. And then this one they maybe turn upside down. These two that maybe, this last one they maybe turn 90 degrees. And that is, there's 2 configurations and 4 of them. So that's enough data. There's 2 to the 4 shuffly ways you could do this. And apparently when you stack them up, the number appears. Is that on the back or something? Oh my goodness. On the back. So how would you build this? You need the kind of, the holes in the pages need to be kind of uncorrelated. And then the back of this card must look like a mess. Yeah, there it is. Yeah, okay. That's sufficiently mad, right? Okay. So what is the pattern? Is there a pattern to this? Could we design a simpler version of this? Oh my goodness. I need to make as many people as possible look at the Murderous Maths website. This is good. I'm concerned that some of the larger holes or smaller holes. No, it's 4, and that's got a corner cut out. So each time, why is it 1/4 that's cut out of each card? Apparently we can get one of the books to understand what's going on here, but let's see what we can work out just by looking at them. So these are kind of quarters that you can see through. Why has each one got to remove 3/4? Oh, there's some overlap and stuff going on, right? So it's 3/4, but they work together in an interesting way. That if you pair together two of them, they still agree in two spaces, not four. Gosh, okay. So there are 8 reasons you might have this card this way up. Or you might flip it over. This one has got, yeah, okay. Something to do with corners going on. And then the final one is out by 90 degrees, which gives you an extra thing. Gives you an extra choice. So these are kind of, what are these? These choices of which 4 squares to remove are kind of, they're selected so that, okay. So Gudjadin designing this has to make sure that the numbers, no idea. These things are usually binary, right? So this is whether or not the numbers got an 8 as part of its binary expansion. This one is, what on earth? These things are usually binary. That means it's usually a card that's got all the odd numbers. What on earth have you done, Gudjadin? So this one is ones that have, what's the link between these numbers? So what can I see? 3, 4, 7, 8. And then, no, not the same numbers, but plus 8. That would be too easy. What is this? This is great. I love the way the numbers on the back aren't even in a recognisable order. It just turns out that this properly encodes the correct one for each orientation. It's absolutely great. So something I've noticed is that these 3 cards are either the right way up or the upside down, and either way, the lower left and upper right corners are obscured. So it's kind of the 90-degree switch. But there's no reason they have to be like that. Oh yeah, for the 90-degree switch to work. So for this technology down here, where at the last stage there's a 90-degree switch. For that to work, the things that are obscured in, it has to switch out 8 possibilities for 8 other possibilities. So one way round, 8 of the cards have to be not selected no matter what you were doing with the other 3. And then if you change it, okay, so you need some sort of structure like that in terms of... The main question for me is, why is it been designed like this? The cards are so weird. Oh, brilliant. Okay, love that a lot. Something to think about. No, one more go. And chat, can you tell me what's going on with these numbers? This one, I feel like I understand. These are the numbers 1 to 8, chat. But for the other part of the magic trick, we have numbers that are large-ish down here, 5, 6, 7, 8, but then 11, 12, 14, 15. So there's not quite, oh goodness me, 9, 10, 11, 12, 13, 14, 15, 16. Oh gosh. 13, 14, 15, 16. No, I've got nothing. When I first saw this, I thought, this will be like the binary card thing that you sometimes get in Christmas crackers. You might have seen this before. You're presented with a set of cards, and you're asked to select the cards that have your chosen number on, and then which ones you've chosen is a kind of binary encoding of your number, and the cards have been carefully designed so that each one really corresponds to the question: does your number have a 1 or a 0 in that bit of its binary expansion? So that selecting it or not is just telling the person whether it's got a 1 or 0, and they can quickly add up the numbers on the cards. So if it was that, then you'd see cards that look like this. So there'd be a card for odd numbers, and if you selected that card, then you're saying my number's odd. And then you would see a card that had maybe this is an interesting pattern. Yeah, Mountain Ash says maybe it's been slightly roughed up a bit to make it look more magic. It's part of the show, isn't it? 2, 3. It's slightly harder than I thought it would be. Numbers that have a 1 here, 2, 3, but then 4 doesn't. And that's the pattern that repeats. 5, 6, 7, 8, 9, 10, 9. 9 doesn't because it's 8. No 4s, no 2s, 1. But 10 does because it's 8 and 2. 11, 8 and 2, 1, and then 12. 13, 14, 15, 16. So you'd see things like that. And then for this one, a different combination of half of the numbers. And then I guess there's a card that says whether your number has an 8 in it or not. Nope, this is a 4, and then there's an 8 card, which tells me whether or not your number has an 8 in it. So that would be something like the large numbers. And this will be the ones that have a 4 in. So they start 4, 5, 6, 7, but then 8 doesn't, and then there's a long stretch that don't. 12 does because it's 8 and 4, and then 13, 14, 15, and then 16 doesn't because it's just got, I don't know what I'm doing at 16 actually. Maybe I'm stopping at 15. Yeah, maybe I'm stopping at 15. I'm losing confidence. Oh, I guess I could write the number 16. So at the moment, if your number is 16, you select none of them. So maybe I could get around that by writing like a 0 or a 16 on all of the cards. You select all of them? No, that's currently what you do for 15. Selecting none of them has to be 16. Okay. Yeah, so if you're thinking, okay, my magic trick on the screen is now ready. This is the sort of tidy version of what I think is going on for Kjartan's trick. It's possible that Kjartan's trick is also doing something tidy, but here's a kind of tidy version of this trick. You've maybe seen this in a Christmas cracker or something, or just because you've seen some maths tricks before in somewhere else. You're presented with 4 lists of numbers, which you just saw me work out very slowly. The trick works like this. You tell me which lists your number appears in, A, B, C, or D, or none of the above. And then I work out what your number is. Oh, I'm sorry, no, I use magic to infer what your number is. You can play this in chat if you like. If you think of a number think of a whole number from 1 to 15. Think of a whole number from 1 to 15, tell me which lists it is in, and then I should be able to work out what it is. I've used binary to make my lists. While you're having a go at that, I'd say there are other ways you could. So how would you rough this up a bit if you were trying to design this to make it a bit less obvious what's going on? How would you rough it up? Possibly you could combine some lists together, because I just need the information of which of these real 4 lists you're in. So maybe I could do some combinations of lists. Can I combine them in any obvious ways? So I take the lists A and B, that information. Maybe I show you a list that's A XOR B or something. Mary's number is in all the lists. That is the number 15. Mountain Ash's number is in lists A, C, and D. The A tells me that its binary number ends in a 1. The lack of a B tells me that the binary number doesn't have a 2's. And then C and D, so this tells me that the number is 13, which is here, not here, here and here. Good. Herb's number is just in D, which tells me that it's not in list C or A, which tells me it's the number 8. which is there, which is faster than checking the lists. Maybe this is a good way of storing things or something, who knows. It's a bit like a... Yeah, let's try and work out that use case. Let me think. You're trying to store 15 objects and you want a really descriptive code. So you have 4 colours of stickers that you might stick on the thing, and that tells you exactly... No, wait, because I'm storing my thing in multiple places. Oh, I've confused myself. Good. Okay, how would we rough this up a bit? So this is the version that I've seen on Christmas crackers or whatever. I want to kind of rough it up, make it look a bit more magic, like Mountain Ash said. I've decided I'm not going to understand the predictor cards, I'm going to design my own. So at the moment, A and D look the most obvious to me, the least magical. Is there anything I can do to preserve that information? I guess I want to show you 2 weird lists, and then from that recover the information about whether you would have been in list A, and separately recover the information about whether you would have been in the list D. My first guess is to do a kind of A plus D, A minus D kind of thing. Where, let me think. What would that do? So if like an and or an or a not, I suppose, to do some sort of logic gates on it. So if I show you a list that's A and D, that sounds like a disaster. Maybe if I show you A minus D and D minus A, those are going to be quite short lists. How can I combine these together? Okay, I think we found a good question. How can I combine these 2 lists together, A and D, to do something? Yeah, swap out values randomly. I think I want an example. Still have a binary number associated, but it wouldn't be obvious. Yeah, I think I want to disguise the information, but binary information is quite a good idea, and it leaves you these nice lists. Then I need a table. Okay, so the properties that my list has then is something like, to make sure I don't have any clashes. If I just do it randomly, then it might go badly. I might have 13 and 11 appearing in all the same places. I need to make sure my lists are kind of uncorrelated, so that I think this is the case. Any 2 lists have exactly 4 numbers in common. That might be it. And then I can make a table at the end for a lookup. Maybe I should try and codify that. Or maybe I should mess around with this idea to make 2 different lists. If I kind of show you the mega list of both, then a bit worried. Too many things will be in there. What if I take... So let me do a kind of Venn diagram for A and D. What have we got? We've got 1, 3, 5, 7. They only appear in A. We've got 9 and 11. They appear in both. And we've got, and 13 and 15. They appear in both. And then we've got 10, 12, 14, 16 over here. So at the moment I've got list A and list D. And I've got all the other numbers floating around outside that don't appear in either. So I think I'd like to make my list, to disguise this a little bit, I'd like some sort of clever combination of these numbers. And the thing that's jumping out to me is maybe I show you A, D, maybe I'll show you the outside. Yeah, what's that like? If I go 1, 3, 5, 7, 10, 12, 14, 16, then if you're in this, then that tells me you're in exactly one of A and D. I still need to know. And then maybe if I show you, what's my other list then? So maybe my other list is just 1, 3, 5, 7, 9, 13, 11, 9, 11, 13, 15. If I show you these 2 lists, can I recover the information? It's going to be a bit of a logic puzzle for me, but if you're in both, so this is Gosh, what is this? This is A XOR B. This is A XOR D. I was calling it list D. And this is just A again. So if you're in both, then you're in A and not D, because you're in one of them and it's A. If you're in the first only, then you're in exactly one of them and it's not A, so it's D. If you're in the second only, then you're in A and D. And if you're in neither, then you're not in A, because you're not in this exact copy of A. And you're also not in D, otherwise you'd be in one of them. Okay, so we can recover from these two lists. We can recover the initial information. What I've done there is I've replaced D with D XOR A. Random in a thoroughly non-random way. I missed that in chat, that was a really good phrase. Okay. So I think I should be able to recover information even if I've replaced lists with XOR. And I had a choice there about which one I kept. It kind of broke symmetry. So I can XOR some lists. So maybe when I see Jarton's lists, there's some XORing. That looks like my first list with small numbers on. Oh no, with this one with large numbers. It's flipped as well. You can flip and show people the negative of the numbers because they're both there. They're the other way around. On these cards, it's which way up it is. Okay. So you can do that as one bit of information. And what is this list? So there's some sort of combination of logic gates has gone into this list that involves skipping 11, 15, and 16. Maybe? And correspondingly, mirror image. Is this what's going on? 16 and 15, 1 and 2. The two smallest and the two largest. And then 3, 4, and then missing 5 and 6. This is missing 11. This is missing nothing. Nope, okay, that's not what's going on. This weird asymmetric list of numbers. I still don't know what these numbers are. This is brilliant. I've made a slightly more interesting version for myself, I think. I've replaced my card that's large numbers with card that is some small odd numbers and some large even numbers, which is slightly more fun. Kind of want to do some XORing then. So maybe I can undo a string of XORs. So I can undo a string of XORs. So if I presented some really weird cards, some really weird binary questions, yes, no, that I'd taken these beautiful ones and just XORed pairs of them, replacing one with an XOR of itself. Then maybe I can still work out the information at the end by undoing all the XORs. Okay, that sounds like something I should go and design. XOR a bunch of cards, design a weird version of this, and then put it in Christmas crackers. People will have to learn a more complicated system for extracting the binary number that you were first thinking of. Yeah, this is a different way of thinking about it, right? You've got 4 switches that are either on or off. 4 switches that are either on and off. And then you can do some quite complicated wiring over here to translate that into questions. A wiring that you're allowed to do is an XOR, retaining one of the bits of information. I don't know the symbol for an XOR gate, so I'm going to quickly look that up. It is apparently one of these. Oh, and then down and then curved like this. Okay, XOR. Which here would be true, which I think I'm doing this. And I think you can work backwards from this. If your cabling always looks like you replaced a pair with the value and an XOR gate, then I think no matter how the lights line up at the end, you can always work out what was going on before by working backwards. Suggestion in chat, which I think I'll read. So this has now got a more interesting pattern of lights that's not obviously related to the thing I had at the start, but then I can work backwards. Say the XOR is true, so one of the lights was on, and it's not that one first. Write the number twice on the cards where the output is a 2, then you have an odd largest number, which is what I've always wanted on those Christmas cracker things. How did the Christmas cracker... Hang on. So odd largest number, I'll get to try and read in a second. What do I do for 16? Do I put it on... For me, I have to put it on none of the cards, which is weird. Oh, maybe I'm asking you to select the ones which your number's not on. Invert all of them, select the ones your number is not on. So trinary. Trinary, for people who haven't met it before, is not as serious as binary. The idea is that you do binary by replacing all the 2s with 3s. So you count like this: 1, 2, 3. You write like this. 4. You write like this. 5, 6, 7. Where kind of the carry happens after the digit 2. Red and white and blue. So, card game based on this. You need people to be able to reveal trinary information, maybe? So you've got this card with some numbers on it, and you kind of want them to do something like select it, or ignore it. Ignore it if it doesn't appear. Select it if it does have the number on, and kind of like double select it if it really has their number on it somehow, which... What's the suggestion that if your number appears twice on that card? No, this is not right, is it? Because then there's 3 things you could do with a card. Based on whether the middle digit of its 3-digit trinary number is 0, 1 or 2. This feels quite binary again, because I'll have some numbers and some bold numbers. I guess it is trinary because you could not select the card. Maybe this is fun. It will convince people that it's a different trick. Okay, let's try and design this. So, I think I'm brave enough to go to 9. My cards are going to look like this. There's going to be 3 of them. I guess I'm going to 27. Oh, so much data. Okay, so the first one. This card is designed so that you are supposed to ignore it secretly if your number is a multiple of 3. I would like you to select it if your number is 1 more than a multiple of 3, and I would like you to mega select it if it's 2 more than a multiple of 3, which I will indicate to you by underlining. So hang on. So not the multiples of 3, but then yes, very much. Those ones, 7, 8, 9. I think I can go, how high can I go on this? Well, I'll leave that question for a second and just write 10, 11, 12, 13, 14. I mean, this card could have loads of things on it, couldn't it? But there we go. And then for B, harder card to design, I'm thinking about the middle digit of my 3-digit trinary number. I guess I'm going to 222, which is one less than this thing, which is 27. So I'm going to need a bit more space. 15, no, not 15, 16. This is a bit like FizzBuzz. If you've ever played FizzBuzz, 20, 21, 22, 23, FizzBuzz, 24, 25, 26. Okay, the dream, right, good. Okay, so the middle number, I want to think about whether that is 0 or 1 or 2. And these are going to come in sets of 3 in a row. So it's going to be something like 1 and 2 don't, but then 3 does, 4 does, 5 does. And then by 6, we get to the point where it carries over to 2 and a 0. So I want that to appear here. I want that to appear here. That's like, seriously, the number 6 has a 2 in that position, and then 7 and then 8. This is going to be such a good trick when it all comes together. It's going to be really good. And then there's 3, I'd say 3 off 9, 10, 11, 12, 13, 14, 15, 16, 17. and then I take 3 off. 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. And then finally, want to think about multiples of 9, or things starting at 9. 9, 10, 11, 12, 13, 14, 15, 16, 17. But then 18 has got 2 9s in its trinary expansion. 9 plus 9 plus 0. Oh my goodness. This was a great suggestion, Mountain Ash, that I think I'm butchering, but we're about to play a game, so that's always fun. Okay. Let's test it out. Chat, help me out here. This is going to revolutionise the Christmas cracker industry. So it currently goes to 26, which is an even number, so that's different from any Christmas crackers I've ever seen. Mountain Ash has seen, I think, the opposite game, but never mind. I would like you to think of a number. Think of a number from 1 to 26. These could be letters of the alphabet. Missed opportunity. Think of a number from 1 to 26. Oh, we're definitely doing this with numbers. With letters. Definitely do this with letters. But for now, think of a number from 1 to 26. I want you to tell me which of the lists A, B, and C is it in, and say the letter twice. Say the letter twice if it's underlined. Yeah. So, for example, if you were thinking of 2, you would say AA, and then not B, and then not C. This is a great game. This is fantastic. We've designed an amazing experience. So then you see Herb in chat says BBCC, which means Herb's number is not in this list. It's underlined in this list, and it's underlined in this list. And you can kind of logic your way through it. Let's say underlined in this list means it's a large number, so I should look over here. Underlined in this list tells me it's for one of these 3, and then it's not in this list, so it must be 24 Herb. But said differently, that's because Herb's number is this in trinary, which is 24, because it's 2 9s and 2 3s. Oh, this is great. We designed a thing. I feel like we've genuinely done a thing. Mountain Ash. Let's try and do Mountain Ashes with trinary, since it was your idea. This is your number in trinary because it's got 2. It's kind of backwards in trinary, 2 1 2, but that's a palindrome in trinary anyway. Oh, I'm hitting my stride. Here we go. 18 and 3 is 21, and 2 is 23. I think. Let me check. Underlined in the first one. Appears but not underlined, and then appears and is underlined. We did a thing. You picked quite similar numbers, people in chat, with radically different trinary expansions. Good, right, okay. Oh, we found a way to make new cards. Definitely want to do this with letters. I think this would be fun with letters. I don't know what I'd say about the lists though. So what's the? I haven't quite got. In chat, I can make you say the letter twice, and we joked about selecting it extra much. I think what's missing is a kind of physical thing that you ask people to do. So maybe it's something like it needs to be something like, if your number is underlined, then select. How do you select twice? The problem is that lots of these with the selection is kind of very binary in feeling about you either do something or you don't. I'm thinking you tear up the card, but you either tear it up or you don't. You need kind of 3 things that you want. Ooh, capital letters versus lowercase. That's how you could report it to me in chat, right? I'd like a physical thing I could take to a school. And I've seen some XOR technology, so I think I should do some weird XOR stuff. Although, does that work with trinary? Maybe not. Yeah, I don't know how to XOR. We need to reinvent. Before I was going to XOR to make things harder, right? Because I had two lists like this, and my data was you're either on the list or not. I think we need to invent a new sort of logic if we want to obfuscate our cards. If we can do that, then I think we'll have invented something really complicated. But also quite hard to invent. Yeah, some other list that's not so obviously based on trinary. Oh, am I being dim? Can you just... Is there a way to do this where you just permute the numbers and then do a lookup at the end? Yeah, that's maybe an easier way. Rather than XORing lists or doing anything, I do some sort of weird mathematical operation on your number, like multiplying it by something with an inverse mod 27, multiplying it by some weird number to get a kind of different number. And then that's the things that appears on the cards. You do your selection based on that. I infer that number, and then I undo the maths operation. So I'm going to play this, but with f of x instead of x, where the things that you're selecting are like weird, whoa, crikey, f of x things labelled weirdly. Just kind of mix them up a bit, but in a way that can be unmixed. Maybe that's one way to make this puzzle more interesting. Going to practice that a little bit. So these cards are a little bit cumbersome because there's quite a lot of stuff on them. Let me just copy paste to make a smaller version. Do I want to make a 2-card version? I feel like a 2-card version is actually going to be quite boring. So what do I want to do? Maybe these are letters and I've sneakily done a kind of ROT13 kind of thing. So there's cryptographic things you can do. One of them is called ROT13, where you replace each letter with the one that's 13 letters afterwards. It's called ROT for rotate because you're imagining that the letters loop back around again. ROT13 is easy to undo. And I actually think it's not going to be too exciting on these because they already have a nice repetitive structure. So if I do a ROT13, then all these large numbers turn into small numbers because they get rotted by 13. I kind of want to do something a bit more fun. What's a good way to obscure numbers? You have the sequence of numbers 1 to 26. Apply a function that I can undo, but which looks really weird. That's a good question, in a way. The one thing I thought of is multiply them by 5, mod 27. Because I can undo that by multiplying by don't tell me, the inverse of 5 mod 27. Which does exist, right? Yeah, 5 and 27 are co-prime. I'm going to be fine. Yeah, something sensible like machines, that'll be fine. Okay. Maybe I'm not going to obfuscate these. I might list them out as the alphabet though. Let's see what those cards would look like. So let's see if I can do the alphabet. Off we go. So just translating them into letters. Sunday chill maths, isn't it? C, D, E, F, G, H, but I've got behind on this one. D, E. And I thought doing them all at once would be fun, but I'm regretting that already. E, but then skip F, and then G, skip H. What is this sequence? This sequence is great. I love this a lot. A, B, but skip C. D, E, skip F. G, H, skip I. J, K, skip L. M, N, we're up to here. M, N, skip O. P, Q, skip R. S, T, skip U. V, W, skip X, Y. And today, apparently, I'm saying Z. So there you go. C, D, E, F, G, H. This list will be H. I'm going to switch numbers and letters just to see if that makes it look more fun. I, J, K, L, M, N, O, P, Q, R, and then it skips S, T, the 20th. Oh dear, I think I've got out by 1. Did I miss L? Oh, this is not my highlights, is it? H is the eighth letter. I, J. I don't have to do them in order, but here we are. I, J, K. And then, yeah, I missed L. L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And then there's a long string over here. So A to H, and then I, J, K, L, I, J, K, L, M, N, O, P, Q. R is the 18th letter. R, S, T, U, V, W, X, Y, Z. They should each have the same number of letters on. My last one looks a bit shorter. 4, 5, 6, 7, 8, 9, 10, 11, 12, 18 is 2/3. Good. And I need to do the underlining. And here it's like 3, and then 3, and then a big skip, and then 3. Here we go again. The 17, I need the halfway point. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. Right, do I like this more or less than the numbers version? Advantages. Looks weird. Nobody would think of using trinary for these. We've done a kind of simple number to letter substitution. The numbers version was too cool. Oh no, we're on letters. We're on letters. And some of them are underlined. Or maybe they can be in bold. Advantages? Maybe you could now shuffle them to spell magical messages. They're part of the trick. Like, ooh, this one says, I'm not good enough at anagrams, apparently, to do an 18-letter anagram in my head. Oh, well, there we go. Bad men. And if your card is in the bad men card, then you select that. And also look at some underlining. It's not the best magic trick at the moment. But there we go. The Christmas Cracker number one wasn't that good either. Right, cool. Not Kajartin Boskett yet. Okay. I'm backing up slightly. I feel like I've made a thing worse. We made a cool thing, and then my twist, not as good. Let's go back to predictor cards. Or even other tricks. Is this the thing that I saw on the Discord? No, okay, what's going on here? Yeah, so I've seen this before. This Get Off the Earth thing is classic. Oh, 1898. That is probably a classic. And it rotates. Did you see that happen? The middle bit rotates. And the number of people in the picture changes. If you look over here, there's count 2 here. And the middle bit rotates a bit, just a little bit, and you get fewer people. Weird. I sort of want a version that's not animated, but hey. So here's a football team with 11 people on it, and then, oh my goodness, they've slightly permuted, and there are now 3, 4, 5, 6, 7, 8, 9, 10, 12 of them. Wow. And yeah, this one is weird because they all look, they're not obviously missing bits, right? Why is this logo moving? Is that part of it? What's actually moving in this GIF? Kind of want a before and after picture. I think the logo is distraction because the bottom half's not moving, right? Yeah, it's the top. I can't drag it. When I've seen this before, the idea is that the people are sliced at different places. And in the new version, everyone is slightly smaller. How would I illustrate this? Maybe the logo's there to stop you counting the feet, but also there's some sort of ambiguous feet around. So if you look at his feet, in the first image, it's the professor's feet, which don't count as a player. And in the end, there are player's feet. So this player has gained professor feet, which previously weren't part of a football player. And then if you look at them, they started over here. And it is this one, it is this guy, isn't it? The yellow, the legs. There they go. No, it was this one on the middle. Sorry, it was this. Tracking them. I don't like the shuffle. Oh dear. Because what are they missing? So in one configuration, they're missing something relative to the other. Good. Right, good. What's this sliding blocks? Oh no, it's different. Okay. Good puzzle. Love it. What do I want to do next? Chat. We've got maybe 15-20 minutes. I've seen the 8 Queens puzzle before. I would quite like to do this mind reading thing. If you've already been on the Murderous Maths website and I'm missing something great and fun, let me know. Otherwise, I'm just going to keep working down random things like this that catch my eye, like this mind reader. Okay, it's about choosing numbers. I think I actually remember this illustration of someone with the 15 of hearts from one of the books. Anyway, choose a random 2-digit number, e.g. 28. I know I can't think of anything except 28. Add the digits. 3 plus 7 is 10. Subtract the result from the number. Oh, from the original number. Interesting, because I've now subtracted my units digit and I've subtract the result, and I've subtracted 10% of my tens digit. So I'm now at 27 because I subtracted 10 from 37. Done that, then click here. Okay. Look for the picture above your number. Oh my goodness, here we go. Interesting structure here. Yeah, okay. So I had 37 take away 10, which is 27. I've got this picture. I'm going to click here. Oh my goodness, it's this picture. So I think half the puzzle here is hiding in this table, which you can have a look at. I like this a lot. This is a good version of the puzzle. Oh, they're permuting this as well. Wait, hang on, this is brilliant. Hang on, this is great. So that one's taken me to thoughtreading2.html. So always do that. There's some sort of fun randomization going on this page. But then when you click through, it's got a little variable here. It's keeping track of something, like which variant of the pictures it's shown me. Fun times. Okay. This is slightly better than it could have been, right? This time it's showing me this one above the number 9. There he is again. How have you done this? What HTML wizardry is this? It's got 2 layers, right? The maths wizardry and then the HTML wizardry. Ooh. One of these. If I change this. That's not doing what I thought it does. Maybe I don't speak HTML. Why is there a question mark 3 on the end of this URL? How does HTML work? Does anybody know what's going on? Okay, now I'm looking at cards. It is showing me cards. It had an HTML 0 on the end this time. Maybe I'm approaching this the wrong way, but I'm way more interested in the HTML tags than I am in the maths puzzle. I don't know how do websites work. What's going on as well? What's going on? Inspect source. What's going on? Help. Yes. This website seems to be made of website. Good. Right. Love it. Background again. Tricks and games. Good times. Want to meet the characters? Mostly I remember the aliens. What were the aliens called? Golox from Planet Zog. It is worth thinking about HTML. Okay, maybe I don't know enough HTML. Good, okay. Fun stuff to make it do. Mostly fact. Oh, no, there's the predictor cards again. Some dice. Magical self-assembling cube. Did somebody make this? Mountain Ash, did you make this in the Discord recently? How to make 4x4 magic squares? I would love to make 4x4 magic squares. Oh, okay, but this one, well, it's got X in it. 4 horizontal and vertical lines, the 2 diagonals, and the 4 corners. Ooh. Is that 24? Okay, and some other ones that add up. Okay. Oh, this is my diagram of 24 ways in which you can add up the numbers and get the same target. Any target number can be chosen for the square. Best between 20 and 15. It's got a variable in it. Numbers in yellow squares are dependent on the target number. Okay. Take off 20 and put it here so that the sums work. There's a degree of freedom left over in this magic square, which is quite nice. Hang on. That degree of freedom is precisely adding. So it's uncorrelated. It's adding. If you increase x by 1, it increases obviously every row and column. And then maybe all of these patterns are also uncorrelated with this. They contain 1. Hey, look, it's the same technology, right? This shape we've seen before as the holes in the predictor cards overlaps with this one in exactly one place. This is good. So is this a famous magic square if you choose the number 14? I think it might be. So this is just a regular 4x4 magic square, adding up to 34 in each row, but using numbers 1 to 16. If you put the number, if x is 14, I think it's using every number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then there'll be a 13, 14, 15, 16. That's those numbers in the magic square. That's always the weirdest bit of our magic squares, I think, the idea that you have to use particular integers to do it with. If you drop that, then you can add to your magic square. And the technology here is to add at these 4 points to increase those numbers, because that will increase all the rows and columns by 1, and also all of these patterns by 1. And some other patterns, right? So yeah, I was just thinking this one, but less symmetric patterns, probably. I guess they won't add up to the target sum though. Oh, so this is weird, because then the original magic square has to do all of these things. So that's quite good. Oh, link in chat. Yep, okay, here we go. We're doing it. I've got so many pages open, it's great. I should maybe get the Magic of Maths, because this is the second or third reference to that book. This is the basic 5x5 magic square, and then edit these numbers, which are actually on a nice kind of. There's a pattern to those as well. Fans of Latin squares. Let's see what's going on. Oh my goodness. If you want each line to add up to 80, add loads to that, which is nice. Okay. Another look at the way the numbers are set out in the original square. Okay. That uses all the numbers 1 to 25, which is nice. If you follow the numbers around in order that they appear in this pattern. Oh my goodness. Goes off the top and comes back on the bottom. Where have I seen that before? Then goes off the right and comes back on the left. 1, 2, 3, 4, 5. Oh, once the first 5 numbers are in place, there's no empty space but the 6. So go down and then keep going. Okay. That's nice. You go round 6, 7, 8, 9. And then this is good because each row is a kind of bit of an arithmetic progression. One of the perks of knowing that to actually get introduced to magic squares a lot. Yeah, well, again, this is what's happening now, I guess. I'm getting introduced to some magic squares stuff. I haven't seen this. If you work round in diagonals like this, looping back around, then you make a magic square. It kind of does make sense. So work on 3x3. What do we do for 3x3? Well, of course it works for 3x3, but let's do it for 3x3. So it'll be 1, 2, 3, and then you want to go under 4, 5, 6, and then go under. Do I go back and go under the original one, or do I go under here? Kind of want to go. Does it matter? Maybe it does. I'll go over here. No, I've been step up. Maybe I'll go under here. And then 16, 15, 14. I've been step up. I didn't understand the rule. Good, check. What was this about putting the 6 under the 5? Just go over the top, because I played the 1. No space for the 6, yep, because I already have a 1 there. Put the 6 under the 5. Now consider, continue. 6 to 10 goes around with no space for the 11. So the 11 goes under the last number, which was 10. Oh gosh, okay. Maybe I don't understand what's going on. If you put it in the middle of the top line, it shows the diagonals work, and the 4 corners and middle number add up to the total as well. Okay, so I didn't follow instructions. I'm going to have another go. So after here, I've run out of space. Oh, I should drop underneath the 3 and come back over here. I did not understand. And then 5, 6, and then drop the 7 onto here, and then go off the edge and get 8 and 9. And now I do have a magic square. Yeah, because everything adds up to 15 in the columns and 15 in the rows. Okay, thanks, Charity Basket. I have a magic square now. My diagonals do not work. This diagonal in particular is terrible. It adds up to 6. I still feel quite magic. Okay, so if you rotate it, what was going on there then? So can I translate this into maths? I'm sorry though, like, you know what I mean? Like, the rule is to go that way, looping around, unless you can't, in which case go down by 1, and then keep going. What is that? What pattern is that describing? So, what pattern is that describing? Something like this. You've got this, but then you've got a bit where you go sideways instead of going diagonally up. And then you go around again. And then you'll hit here. And you'll go sideways 1 step earlier? No, same point, right? Same point? Where do they drop? So I drop down here, and I drop down here, and I drop down. I ran out of space twice. 7, 8, 9. 1, 2, 3, drop. 4, 5, 6, drop. 7, 8, 9, and I'm done. But it would be time to drop and put the next number afterwards. So these will happen in different columns. Moving to the left. Now, what's the geometry here? What is going on? I have, so number, this kind of, I want to understand the structure of what's going on with the chain of where you're writing things. The suggestion is you go round like this, and then eventually you'll loop back round again. You loop back round, yeah, you loop back round here. And you'll get to this point, right? And then you'll go across. So I think the dropping would always happen in the same column. I'm not correct though. I'm not correct. Dropping doesn't happen because you actually drop down. You drop down instead of dropping down to underneath where you would be, you drop to underneath where you are now. So you drop down like that. Okay, improved diagram. So you start somewhere, doesn't matter where, and then you drop down and keep going. You get round and you drop down, and these drops happen one to the left each time. So you will go around on this. So then, hard question, why does this cause all of the columns and rows to add up to the same thing? Well, there's kind of a nice way that this line of jagged drops itself is going to travel around and get back round to where we just were. This kind of pattern is going to keep going. Itself is going to go round and loop back round again. That's quite nice. What does this mean for adding? I guess each number on the way down is a certain amount larger, like a predictable amount larger, as you go around. If you're making some magic massive square, I'm imagining. There's a kind of predictable pattern to these. It's got to be an arithmetic progression for what's going on in these. And then maybe my understanding is something like when you get to the drop, the drops come around like this. And then instead of being that predictable difference, the difference is just, it's just +1. It's the next number, because this is where I was doing the drop, and it comes around once, because the drop is moving backwards slowly until it gets all the way around. That's about the differences though, not about the sum. It feels like all the numbers to the right should be one larger. But I guess it's wrapped so that eventually, as you move to the right, everything goes up by 1, but also the whole thing goes down because of the jump. Am I close? Yeah, you get... It kind of feels like as you move up, so going from this... Going from this column to the right, I go from 4 up to 5, and I go from 8 up to 9. Wow, that's too large. The numbers are getting larger, but also I go from 3 to 1 for a complicated reason to do with you've got off the end of a loop, and you're looking at what was a loop back. So this goes like +1, +1, -2 as you read up and diagonal. Mumble Mumble Magic Square. I think we can do better than Mumble Mumble Magic Square. So on this large one, as you go round, each time as you compare one column to the next, you'll mostly be looking at numbers that are 1 larger, because your plan was to wrap around and go up by 1 diagonally, except for the kind of jump discontinuity bit here, different colour, where instead of going up by 1, you'll go down by n-1, because the number there is actually n lower than... Yeah, you kind of go up by 1, but also down by n, because it's the previous loop around. So you get a load of +1s, but also a +1 minus n, which perfectly cancels out. So all the +1s go up by 1, and then minus n, because you have a jump. So long as you make sure your jumps, where the numbers, well, I was expecting here to go from 3 up to 4, the next number, but it's jumped out by 3 because that's the previous bit of loop where I was doing some sort of jagged jump like that. Well, goodness knows. There we go. I don't know how to label this bit. I guess I fell down and then I went off the page. It's over here somewhere. So to make sure your jumps are in different, make sure your jumps happen in different places. I'm thinking of these as kind of discontinuity jumps where you go reading diagonally upwards, you don't see the next number. It's now impossible to read anything from that diagram. Make sure these jumps happen in different places. Doop, doop. You can make sure that they move left by 1 each way around. That kind of works. Okay. Mystery squares. Oh no. Okay. I think I've worked out why the rows and columns might be nice. Well, why the columns might be nice. I guess then the rows are doing almost exactly the same thing, but I circle the things slightly differently. Yeah, I don't really want to think about that. The diagonal motion is good because it covers shifting from one row to the next row as well as shifting from one column to the next column. Okay, it's lovely. I don't think I've seen that before, so I've learned something. So that's nice. Excellent website. Thank you for the recommendation, Mountain Ash. If you've got recommendations for future Chill Maths live streams, do let us know, either in Twitch chat or on the Discord. I've said us because it's a community. Let us know in the Discord or on here. Has been fun. We've hit 4 o'clock, which is the time that I stopped doing this. Go back to the rest of my bank holiday weekend. Enjoy your bank holiday weekend, everyone. If you want to see more of this, I was on murderousmaths.co.uk, an excellent website that is somehow free. So, Site of the Week 2001. That's only got better. You too can. We didn't even go to the bit that says "haha, foolish youth," which might have been like PowerPoint on Fibonacci. Ah, my goodness. Ah, Fibonacci stuff. Everyday maths for grown-ups. Okay. Pans. You too can have fun on the Murderous Maths website. Yes, there's even a link to Whitby. Okay, have a good weekend, everyone. Take care. I will see you around. Is there anyone who can raid? I found out about raiding recently. I don't know how to raid. Okay. Maybe another time. Good. Right. Okay. Bye.